Hello there, moving on to 8.3, taking a look now at a special type of angle called an inscribed angle. Again, don't forget to make sure you have that cheat sheet ready for you to fill in some of these theorems that we have. And let's get started. So we need some key definitions here. As always, there's so much that's new to us. We need to make sure we understand what different parts are that we're talking about. But we're talking about inscribed angles in this section here. So clearly we need to know what that means. So an inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So in the last one we talked about the central angle, and that's whose vertex is on the center. An inscribed angle has its vertex sitting on the circle itself. Okay. Then we have its intercepted arc. And so this is the arc that lies in the interior of an inscribed angle that has no endpoints on the angle. So let's take a look at a picture of that, okay? So this is what I meant by it's the inscribed angle. So we can see here its center, its vertex is sitting here exactly on the circle. That's different from the central angle, which is in the center. This is pushed back a little bit further. And then you can see right here, this is the intercepted arc because when I were to extend the angles through the circle here, this is the arc that's being intercepted essentially, okay? So it's right between the two chords for our inscribed angles, okay? So let's kind of review the terminology here. Are they triangles circumscribed or inscribed? Sorry, that was a truck outside. So circumscribed means it's on the outside, inscribed means it's on the inside, okay? So like for example, this first one here, this is an example of an inscribed triangle. The second one on the right there, it's on the outside, so that's an example of a circumscribed angle, not triangle, okay? The second, third one there, we got a circumscribed, and this guy's an inscribed. So hopefully you understand what I mean when I say the word inscribed. Inscribed is inside our circle, and its vertex is on the circle like that, okay? Alrighty, so here's our next theorem. Make sure you get that into your lovely little cheat sheet. And it's finding the measure of these angles. So now remember when we talked about our central angles, the arc and the central angles were equal to each other. When we're talking about inscribed angles, they are smaller. They're going to be exactly half of that arc. Okay, so this is where students start to mix things up. So make sure you get this written down correctly, okay? To find this angle here, this angle D, it is not equal to angle C. It's not equal to this arc, but it's whatever this arc is, and we're going to cut it in half to get that angle, okay? Or if I gave you this angle, we would double it to get the arc, which is different from a central angle. These are equal. This is a portion of 360. This is a proportional portion of that 360. So these guys are equal. While this is pushed back a little bit further, it is a smaller angle and it's exactly half, okay? So let's use that. I want to find the measure of the blue arc or angle. So in the first one there, I want to find the measure of the blue arc or SEQ. And what I see as the inscribed angle here is formed from that intercepted arc. So I see it's going from here to here at its end. When I get pushed back, I see this right angle. So what we're going to do now is take that 90 degrees and multiply it by 2. Okay, so to go to the arc, we're going to double it. It's bigger. And in this case, we're going to get 180. However, number B, I have this intercepted arc right here. I'm not going to the central angle, so it's not equal. I'm going to go a little bit further here, and the relationship is exactly half. So angle F, that blue angle there, its measure is 40 degrees. Here's our next one, next theorem. If we have two inscribed angles of a circle intercept the same arc, then the angles are congruent. So let's think about this, okay? Let's say these red lines weren't here, and this arc AB was, say, 60 degrees. Well, if I asked you to find angle C, then you would say, okay, well, 60 divided by 2 is 30. So I see that angle C is 30. Well, now let's pretend we don't have the blue line, but I still have that same exact arc measure here of 60 degrees. If I were to now find this guy, the red angle here, and I said what the measure of that is, well, you're going to take 60 and divide that by 2 to also get 30. So this theorem is just saying these two angles, C and D, since they're intercepting the same arc, it doesn't matter where their vertex is. Since it's intercepting that arc, that's going to have to be a 30-degree angle. So if I had a third angle over here, say angle E, as long as its endpoints were on A and B, it's also going to be the same exact measure. So it doesn't matter where the vertex is. All that matters is that it's the inscribed angle, and that's the intercepted arc. All right, let's use that knowledge here. So we know that the measure of angle E is 75 degrees. So what's the measure of angle F? Now you can go through the whole process if you'd like and take that 75 and double it. And then notice that it has the same endpoints D and H, so I can cut that in half. Or just recognize that they're both intercepting the same arc. They're both going to D and H, so they have to be the same measure, which means angle F is also 75 degrees. What you'll notice here is there's two other angles, D and H. These guys here are also going to be congruent because they're going to intercept that same mark EF. Just kind of pointing that out to you. Moving on here, the next thing we have are inscribed polygons. We're going to talk about two specifically, but an inscribed polygon is a polygon whose vertices all lie on a circle. And a circumscribed circle is a circle with an inscribed polygon. So I know that's a lot of circumscribed, inscribed words going on, but what we're going to have is a polygon inside a circle. That circle is considered the circumscribed circle. Now this terminology is important when it comes to definitions, okay? So taking a look at this, I see that this is a five-sided shape here. This pentagon, that is an inscribed pentagon because it's in the circle, and the green circle going all around it, that's called the circumscribed circle, okay? So here is one of the two that we're going to focus on, which is the right triangle. And pretty much what that's saying is that if we have a right triangle inside the circle, the hypotenuse has to be a diameter, okay? And then angle B is going to be, or the inscribed angle here is going to be the right angle, okay? So that's the one that's opposite of the diameter. And that should make sense because if we have ourselves a diameter, okay, the triangle such that this is a diameter, well, this is a semicircle now. And so that's cutting our circle in half. So this is 180 degrees. And if you do inscribed angles, we're going to cut that measure in half. Well, half of 180 is 90 degrees. So if we draw ourselves a triangle such that one side is going to be a diameter, then you're going to have a right triangle. The converse is also true, which if I were to give you this triangle and I say this is the diameter, then we can automatically assume it's a right angle. Also, as well as that we have ourselves a right triangle, then we can automatically assume that this is a diameter. So if this is a right angle, I automatically know that this has to be a diameter based upon this relationship, okay? So angle B is a right angle if and only if that AC, that segment there, is a diameter, not just some random chord. We can still draw random triangles in here. It just won't necessarily be a right triangle unless we have that right angle or one of those pieces is the diameter. All right, the other type is going to be the quadrilateral. With this, okay, the only way we can draw a quadrilateral in there is if opposite angles are supplementary. So think back to Unit 2 when we learned the word supplementary, that means they add up to 180. So in this specific one, angle E and angle G are going to add up to 180. And so what I want you to notice is if I were to find the intercepted arcs of both of these angles so that this kind of makes sense to you, the intercepted arc for angle E is going from D to F, and the intercept for G is F to D. Do you see how it kind of makes up the entire circle there? And an entire circle is 360. So half of those guys is going to have to add up to 180. So same thing happens with these D and F, these two here across from each other. They're going to be supplementary. They're going to add up to 180 degrees. Okay. All right, let's use the knowledge that we just came up with. Let's start with the first one here, letter A. So what I see is that I have a diameter AB. And what that's telling me is that I have myself a right triangle in there because a piece of the triangle is the diameter. And so what I know about angle C is that it's going to have to equal 90 degrees. It has to be a right triangle. So therefore, X has to be 45. For letter B, on the right side there, we see that we have a quadrilateral. All the vertices are on the circle, so opposite sides are supplementary. That means Y and 120 have to add up to 180, and that Z and 80 have to add up to 180. So that's what we're solving for. First was Z, D and F add up to 180, so that means Z has to be 100. And then for Y and, angle G and angle E, they are supplementary, they add up to 180, so Y plus 120 equals 180, and subtract, we get 60. Okay, so that's kind of the big idea with those. Go ahead and hit the pause button, and let's see if you can come up. We're going to go with, is this true or false? Okay, that's what I want you to do for those 1, 2, 3, 4, 5 problems. Okay, so let's start with this first one, angle P and angle Q. So I'm looking at angle P. The intercepted arc I see is TSR. Okay, you can find it by going to the ends of my angle here to kind of figure out where is it intercepting. So it's going from TSR. And I look at Q, and Q's endpoints are R all the way over to T. So that is true. They're intercepting the same arc. Angle SRP and angle Q intercept the same arc. So SRP, that's intercepting the arc here at SP. And then angle Q, well, we just talked about that one. We got TSR, so those are two different arcs, so that's false. TSR is a semicircle. Yes, that's true because I see myself a diameter. So this is going to be exactly half of a circle. That's true. Angle PTS and SRQ are opposite angles. So PTS is this guy. So PTS is this angle. and SRQ, SRQ. So the answer to this is false. And the reason that is because in order for it to be the same, it has to contain the same endpoints, meaning PS and SQ. So the reason is because Q won't match up with P. Because remember, to do the quadrilateral, they have to share those endpoints to make up the 360 degrees. So while angle T and angle R are across from each other, we're missing this gap right here. So therefore, it is not an opposite angle. Okay. All right, PTS and SRP. So PTS is this guy, PTS, and SRP, SRP. Oh, look at that. We were touching both at S and at P. You can see that here, S and P, S and P. So that means it's quadrilateral, and therefore they have to add up to 180. So that guy is true. Okay. Hopefully you have no questions on this. If you do, please let us know, and we'll be happy to help you. Go ahead and get started on that practice.